Okay, so for today, it has been requested that
Is that the only stuff that's going to be on the test, Mr. McKinney? Down in the left-hand corner?
isn't that enough?
What?
Isn't that enough?
Oh, that's plenty.
Yes, and again, what I would be led to believe when we're talking about the gas laws,
We only need to know the ideal.
the ideal gas law, I understand that's plural, but I'd have to review that, but I think we only go over the ideal gas law, maybe the combined gas law, but I don't think Boyles and Charles is on there. Okay, so again, the request was to go over something with gas stoichiometry. Okay, so at some point, you have to be dealing with a gas. Okay, now that might mean starting with a volume of a gas and converting that to a measurement of a solid substance, or you could be starting with a solid substance and calculating how much volume of a gas is produced as perhaps a byproduct. Okay, thank you. Okay, now, when we deal with gas stoichiometry, there's two things to keep in mind. We had illustrated that last time, is that you can use the ideal gas law every time, and what is the other way that you can do this? If it's dimensional analysis and it's measured at STP. Okay, so in this case, I just hit some of your papers with my marker. That's why they'll look like they're purple. Okay. All right. Well, I don't want to use purple because that's what we have wrote down there. Okay. We starting with a gas or a solid?
A gas.
Okay. Oh boy. Oops, not hydrochloric. Hydrochloric. Okay. So what this entails is we're talking about aluminum foil. It used to be called tin foil. It's one of those aspects to where sometimes names of substances never change. And what we mean by that is, if we use the example of lead, okay? You're using writing utensils. It used to be, I need a lead pencil. There is no lead in the pencil. It's all graphite, which is pure carbon. Okay? Or it could be when we talk about with gasoline, okay? That is also that of there's no lead in there anymore. That's why it's called unleaded fuel. But something that actually boosted octane ratings, that's why lead was placed into there. But anyway, one of the aspects that we see here, maybe people don't call this aluminum foil. What else might they call it just because of habit, just like your pencil? It's not a lead pencil. Yeah, you call it tin foil. There probably isn't a whole lot of tin in there. It's right. They just call it aluminum foil. Or it's actually aluminum foil, but people still call it tin foil. So with this, when we are reading the problem, we still need a reaction. Okay, so what would that tell you if hydrogen is being released? Is that a reactant or a product?
It's a product.
Okay, so we have our reaction here. Let's illustrate what's happening. A reaction of aluminum foil, which would just be aluminum, okay, plus what is hydrochloric acid?
HCl.
Might as well put a 2 in front of that while you're at it.
Okay, all right.
Actually, probably not. Actually, yeah.
Okay. The input was to put a 2 in front of there right away.
That's a good idea.
Okay.
Well, one of them's gonna have to be one of them's diatomic, so you're obviously gonna.
Okay.
Give me 2, 2, 1.
No, we appreciate the enthusiasm, but let's see if it works out. Okay.
Yeah, but aluminum has a plus.
Okay. So then, what it doesn't say, just to cut down on time, it just didn't say it was a single replacement reaction. So we already know that hydrogen is over here. Okay. And then when this is reacting with this hydrochloric acid in a single replacement reaction, you don't need to write that. It would probably say it in the problem. But again, we took that out of there just for so you wouldn't have to be writing so much. So we know this is a single replacement. We have a lone metal reacting with a compound here. So that must mean this lone metal replaces something in here. That's where the R comes from. So it replaces the hydrogen. And then what does that put us with over here? Aluminum kicks out the hydrogen. And then what is left over from that? Okay. Okay. Cl2.
Diatomic, and the-
What's diatomic?
1, 2.
is the hydrogen
Shouldn't
not?
it be three? Should be CL3.
I thought aluminum was a plus
Plus
2
three
charge.
charge.
Oh, then I need to get my eyes checked.
Okay. So you're correct. Aluminum does have a +3 charge.
Put a 2 in front of, or a 3 in front of the 2 in front of. No,
I think we're just throwing numbers out. Okay.
No, you gotta put a 2 in front of the ALCL.
You gotta put an H, it should be H2.
Right, because gases are diatomic, and so are halogens. That's right.
Al2Cl3.
Okay.
Oh, wait, no.
Al2Cl3.
No.
Babe, you were fucking.
Okay.
That's my fault.
Put a 2 in front of that.
2, 1, 1,
You gotta put a 2 in front of the ALCL3.
Yeah, because
2, 3, 2.
this is an odd number, but maybe we could leave that as an odd number. But let's try putting a 2 there once.
Oh, you already got it. Just 6 in front of your H2. You gotta get rid of that 2.
We have a 2 here, though.
No, I don't know.
2.
Okay.
What is it?
Okay.
And then you gotta put a 3 in front of your H2. And then a 2 in front of your.
How's that?
Yep.
That look better?
Yeah.
Okay. So now, there's one aspect that we left out at wanting to get to this point first because you have to have a chemical reaction. We're missing some material here. Okay? One, is this, a trick question would be, is this an ideal gas law application? Well, yeah, that always works, the ideal gas law. But do we want to look at this as being measured at STP? The answer would be yes or no.
No.
Okay, so then if it's not measured at STP, how is this hydrogen being measured, for instance? What we mean by that is we can't do a pressure of aluminum, a volume of aluminum, a temperature of the aluminum. Well, you could with the aluminum, but that's not how the ideal gas law works in this gas stoichiometry. Because remember, we've got PV equals N, R, and T. up at this point, the only thing we know
273.
is this here. Okay? So what you need to tell me then is what's the temperature that this hydrogen is being measured at?
402 degrees.
Now, do you have to have that worded in the problem, or can we just put it in the... It would have to be worded in the problem. But my question is, do you want it worded in the problem? Okay. So then, what's the temperature in degrees Kelvin of this gas? 407 degrees Kelvin. Okay? What was the pressure that this was measured under? In atmospheres. But we could say this was under 795 millimeters of mercury. Okay? What does that mean to you then?
So you gotta divide it by 760.
You have to divide that by 760 because you need it in atmospheres. There's that many millimeters of mercury in an atmosphere. So that being said, we'll go ahead and do that conversion. What did I say, 790? 790 divided by 760 gives you 1.04 atmospheres. Okay. We got two unknowns, or do we not have two unknowns?
15 grams.
Okay.
We got 485 liters.
Okay. Because when we look at this, okay, it's easy to get these two confused all the time. Because in yesterday's example, we said you cannot put 22.4 in for this because chances are you're solving for a volume. That 22.4 at STP is what happens when you take that times 273. There's where you're, or no, when you divide,
No, you multiply them.
273 times 0.0.
oh, when you multiply, that's where your 22.4 comes in. That's right. So, now keep in mind it says how many grams of aluminum are used up. So if we started with 485 grams of 485 milliliters, liters, okay, how many grams of this are produced? Now, we can't go straight from this unknown into our grams of aluminum. So therefore, you have to ask yourself, what is the variable N?
Moles.
That's measured in moles. So therefore, here again, do you just want me to tell you how to do it, or do you want to think your way through this?
Just tell us how it says.
Okay, so according to the ideal gas law, you find your number of moles. Now you're in familiar territory. You convert that moles of HCl. Okay. Oh, yeah, 480. Let me say maybe this is hydrogen chloride instead. Therefore, you convert that number of moles of hydrogen. Now you can change it to grams of aluminum. Okay, so with that being said, we've got 485 times 1.04.
And on the other side, you got 33.4147.
Okay, so that was 33.417. 7 rounds that up to a 2. We just continue to round up to the nearest hundredth. Now, once you multiply these two numbers, 485, which is pretty much the same answer, maybe 485 point something, times 1.04, oh, a little more than that, 504.4. Now you can find your number of moles, which means 504.4 divided by 33.42, which gives you 15.10.
Multiply that by
moles of H2. Now, this is only half of our answer.
You gotta multiply that by
2.02.
Because now that we have this measured in moles, we can convert moles of this to grams of this substance. And how many steps are in that problem?
3.
There are 3. That's right. So now let's take that 15.10. So 15.10 moles of H2. So we need to get rid of that mole.
You got
So how do we get rid of that in our next step?
3 moles of H2
Okay?
over 2 moles of aluminum.
Okay? Now, and you're right, okay, when you're saying that. But we want to regroup here and look at this and say we've got moles over moles. Why is that important?
Because you're trying to get rid of
Because now you need, and that's true, it'll allow us to jump from this side of the reaction to this side, but in a mole ratio then, that means this 2 has to go on top and that 3 on the bottom. Okay? So these moles are gone. Now we're in moles of aluminum, which means now we're on the home stretch. Okay? Because for every mole of aluminum, we just do 27. 27 is fine. 27 grams of aluminum. Okay? And it's just human nature. See this every now and then. Someone's going to do that.
do what?
Put a 2 on the bottom there.
They might look at this and say, oh, well, that 2 there, I must have to put this down here because this is moles.
You already accounted for it.
We've already accounted for that. That's why, again, why we call that a mole ratio. Okay? So 27 times 2 is 54 times 15.10. So that gives us 815.15.
271.8.
And we have to divide that by 3. That's not right. 0.40. Okay, so 0.40 goes here. Divide that by 3. And we get 271.8. 271.80 grams of aluminum.
So which one's your answer?
This one. Because now we're measured in this. So how many grams of aluminum? And that's what we got.
Oh, so gas stoichiometry is gas law and stoichiometry.
Combined. Yes. So there's a whole bunch of places and or areas where it's human nature and it's easy to make a mistake. It just is. Okay? And trust me, because every week for this semester with other chemistry teachers across not just this state but across the country, talking about how students can very easily make a mistake here, and the professor saying, you know, I was teaching this. I was there when we were teaching this, but my students just for some reason, it's not computing. We don't want that to be you, all right? Anyway, any questions over this? As you can see, this this is taking up a lot of space and it's a lot of time.
Is there always going to be ideal gas law or dimensional analysis when you're doing gas?
There's always going to be some fragment of dimensional analysis, always. Okay? Because if you use the ideal gas law, you can see there's always going to be some of this. But if it's measured at STP, you can just use dimensional analysis only and be done.
How come we're not doing any molarity on this one?
I just don't think that's important enough to go over.
I feel like what?
Polarity.
No. Is that the one where you like divide by the smallest number and then round to the nearest whole number?
No.
What is that?
Divide by this.
Like you do a thing of equation and then you find the smallest one and you like subtract it.
So that's probably pretty similar how it'll be one limiting reaction, a percent yield, a gas stoichiometry problem like this, a combined gas law problem perhaps, then maybe converting the total heat that it takes, maybe cobalt or gold or any, well, not gold, cobalt or copper to go through the different phases where you're melting it and boiling it and a gas is given off. Probably, oh, there'll be a few organic compounds on there, and then, I don't know, maybe when it pertains to biochemistry, maybe draw a monosaccharide and maybe draw an amino acid or two. Yep. I'm sure if you look back in the notes that you took, you probably could.
What's a monosaccharide?
That's like glucose.
That is just like glucose. Yep.
And we'll be given the chart.
Yes, you'd have to be given the, whether you call it the railroad tracks or the stitches or football seams, all the above. Anything to that nature, you'd have to be given that content.
I say we turn on the water channel.
Okay, so I think what we will do is this will be GCMAY9a, General Chemistry GCMAY9a, and then we're so worried about the weather, so that's why I'm going to stop it here, and then I'll start it again, and then maybe we can put that on the Science Channel to where that'll be General Chemistry GCMAY9b, and then yes. There's really no copyrights with that because it is public information, but I don't control how YouTube works with that. Okay, so that's all I have. We'll catch up to you next time, and we'll have a little bit of weather update from Kelloland here shortly.
Gotta make sure.
Or maybe the Weather Channel. We'll try Kelloland first.